This paper aims to create an accurate 3D representation of satellite imagery without any 3D supervision, by using pairs of satellite and ground images. Our main objective is to tackle the challenging task of generating ground view panoramas from satellite imagery. For the reader's convenience, the central vertical line in the rendered 360-degree panorama frame points in the same direction as the red arrow, just like driving through the satellite scene while following the red arrow. The end of the red arrow indicates the location where the frame is synthesized. Our hypothesis is that 3D geometry plays a critical role in cross-view tasks. In order to test this hypothesis, we first establish a baseline using density-based geometry representation. Density-based geometry learning is capable of inferring depth through volumetric rendering and provides a flexible means of representing geometry. Our baseline approach involves using DensityNet to learn the explicit volume density from the input satellite image. We then render an initial panorama map and depth from the density field, and pass the initial panorama to RenderNet for synthesizing the predicted ground view image. The entire workflow is supervised with adversarial loss, and the entire architecture is trained end-to-end. In our baseline results, while we were able to successfully render videos, we observed that the predicted explicit volume density and rendered depth did not meet our expectations. It was difficult to discern any features or objects within the depth and density due to the significant viewpoint differences between the satellite and ground images, as well as the limited overlap of visual features and large appearance variations. These factors make it a highly complex and ill-posed learning problem, posing challenges in learning faithful geometry. After examining the tasks and satellite ground image pairs, we identified two main factors that may impede geometry learning, which have been overlooked in previous works. Firstly, the sky is an essential part of ground scenes but is absent in the satellite view, and it is nearly impossible to learn the density along the ray passing through the sky region with only adversarial loss. Secondly, differences in illumination among the ground truth images during training make it challenging to learn geometry effectively. To address these issues, we apply non-sky opacity supervision by taking pseudo-sky masks from an off-the-shelf sky segmentation model and using L1 loss functions to supervise the rendered opacity. For tackling the illumination difference in the ground truth images, we inject the RGB histogram of the sky region in each ground truth to the RenderNet during training. This allows the model to focus on the scene rather than being disturbed by the variable illumination. When adding only non-sky opacity supervision, the opacity of the air region becomes 0, but the area between the air and the ground still appears unsatisfactory. While this supervision clears the sky region and the volume density, the inner region between the sky and the ground remains smoothed. This is due to the limitations of coarse supervision in recognizing complex regions, which cannot assist the model in identifying intricate details. Compared to the baseline, the addition of illumination injection can improve the appearance of the rendered depth, but the density of trees appears indistinct, and the density of the sky region remains unclear. Adding both strategies simultaneously resulted in a plausible 3D geometry representation that produces a depth map faithful to the satellite scene. The volume density is noticeably clearer than the baselines, and the inner regions can be easily distinguished. Compared to the baseline approach using opacity loss and illumination injection, our Sat2Density method also incorporates depth information by concatenating it with the initial panorama during the rendering process. This results in images that emphasize regions with depth information and reduces the likelihood of randomly generating objects in areas with opacity equal to 0. As a result, the synthesized ground view more closely resembles the original satellite scene. A work familiar to us is Shi et al. They learn geometry through a height distribution map stored in a multiplane image, and they focus on synthesis ground image rather than video. We expand their work by incorporating camera position changes during inference, enabling they to synthesize videos with moving cameras. Our approach differs from Shi et al. First, our density-based geometry learning, compared to the height distribution map, could represent the scene more real, such as we could render depth and opacity at any ray direction. Then, we incorporated additional techniques to address limitations in learning geometry in our task. By incorporating non-sky opacity supervision and illumination injection, we were able to learn a more faithful geometry representation. Our proposed Sat2Density approach can render videos that are faithful to the satellite scene, with visible road marks and trees in the satellite image, and good temporal and spatial consistency. Overall, our approach demonstrates superior performance compared to Shi et al.'s approach. Last, we show controllable illumination results. It can be found that the sky histogram could easily control the whole image's illumination, while the stuff in the satellite remains unchanged. For example, the road's color was changed by giving different illumination, but the shape remains unchanged. Thanks for your watching.